Hey, so in this video, I'm going to show you how to make a capacitor in this C5 technology. So let me draw a picture for you first, so you know what a capacitor look like in the layout. So remember that at the very bottom level, what is this? This is a P sub, right? That's a P sub. And then you got a oxide layer, and then poly 1 layer, and oxide layer. This is another oxide. And then poly 1 again, then poly 2. Sorry, this is poly 2. So that's a poly 2 layer. So which means the poly 1 and poly 2 has a gap in between, which is a oxide layer. So in that case, what you can do is you can imagine that in the middle is a dielectric oxide, whatever it is. And if you make a certain area over here using the P2 layer, and then you do another layer underneath the oxide layer using the P1 layer. So there will be a common area in between. It's like a two metal plates which has a dielectric material in the middle. You cannot adjust. This is fixed, right? And the capacitor equals to what? Equals to epsilon which over which. So if you have a larger area, you get a larger capacitance. You have a larger D, you have a smaller capacitance. So this is fixed. And the oxide material is fixed as well. So the only thing you can change the area. You change the area, you can change the capacitance. So that's a cross-sectional view. As a top view, what that looks like will be something like this. So you draw a P2 layer here, and then you draw a P1 layer to overlap with this P2 layer. So that area here will be the effective area. And you can create a metal node here, right? And another metal node here to make the connection. So if you look at here, it's something like you have a metal node and you have another metal, drill a hole here and another metal node here. So the capacitor looks like this. So this area is not acting at all, and same as this part. Only this overlapping area is the effective area. All right, so hopefully this is clear. And now let's save this one and let's go to electric VLSI to make this work. And I don't want to calculate that. For example, how much is yeah, let me stop a little bit and continue again since I have something to do right now. I'll come back really soon. All right, so now let's take a look at what I have now. So we have the pad frame, this guy, and we have the schematic for the pad frame as well. So the next step is let's move forward to duplicate this guy, right? So this is a capacitor I have. And now what I want to do is I will show you the area for this capacitor. What is the area? And now let's do a really simple calculation. Won't take that much time. So I'm running to the tutorial right here and go to tutorial 6. And it's over here, and I scroll down to this part, and you can directly ignore all this simulation. You don't have to do this AC analysis. So what we are going to do is you just make a capacitor here and connect it to it and make it work, right? So we don't need to worry about all these things for making it more stable. It takes time. We don't have time to work on that. So let's just learn how to make a capacitor and connect that capacitor to the op-amp. So the area for the capacitor is like 130,000 by scale. And the thing is, we want to know the width of our, because the plan, right? So the plan, where's the op-amp? Op-amp's here. So the plan is we want to put the capacitor back here. So we know the total area is 130,000, and we just need to know the width here, and we can calculate for the length, right? So let's measure that really quick. So for example, we don't want to put the capacitor directly on the top of this guy, so let's make it a little bit smaller than the width here, which is like 240, right? 240, and come back to the calculator. So this guy divided by 240 becomes 240 becomes 5,000. This looks not right because that one, no, this is not right. It shouldn't be 240. Oh, let's measure this again and see what the real value is. From here, it is 240, 250. So the area on the website, the total area of the capacitor should be this. So measure the distance between the two rails and find out the length. This is weird. Let's try to recalculate it. Right, this one, is this right? And divided by 240. So it's 541, which is, I don't know, messed up with the calculation just now. So 541 for the length. And so I will make a new cell and start with the layout first. So let's name it, since I have a capacitor which is cap 10 PF. So now let's make a test cap 10 PF, 10 picofarads layout. So the first thing, now let's take a look at the cap I just made. So make a P2, make a connector. So that's a metal 1 to polysilicon 2 connector. And this is the metal 1 to the polysilicon 1 connector. And you want to keep this area to be 130,000. So if it's 240 in width, it should be 541 in length. So let's make that work in our test model here. Let's come back here. So that's poly 2, that's poly 1, all right? So if I pick up this one, I want to press C to change it to a poly 2 node, but not a poly 2 pin. So change it and double click and change the size to be, that's 541, but actually you need some extension on the two ends. So let's make it 700, for example, and Y size should be accurate. So the Y axis is 245, and press OK. Is that 245? Let's go back and verify. So we don't want to mess that up, since we have to come back to fix it later, which is a lot of, yeah, 245 is fine. And for the cap, it's over here. And you need another one, which is this guy, and Control I. You want to change it to the same size, 700 and 245. Wait, this is not right. So I will press change and make it to a note. And what's the size here? So it's extending to the two sides. I think it should be 700 by what? By 245. It's changing scale. I want this guy to changing scale. 700 to 245. So this is accurate. All right. And then place them together, but you want to make sure the length, since the width is not changing, but you want to make sure the length is correct. So I want to start measuring from here and then stop at 541. Yeah, it doesn't have to be that accurate. Okay, it's fine as long as it's close enough. All right, come back to the ruler mode and press escape. They can delete the ruler. And so this is all right, and we need a connector, metal one connector, and this one should be the same width, which is the y-axis. It should be 245, but we want to make this one a little bit larger than that. So let's make 30. Okay, and I will place it here and right-click this poly tool to make a connection and press F5. No errors. So it's not reporting any errors here. All right, so no errors. The same to this one, and I want to make 30. So X to be 30, but Y to be 245. Boom. And place it in the middle and make a connection and F5. So no problems. And we need a schematic of this guy as well. So come back to here, right click and create a new cell. Let's call it the same name, test cap 10PF, but this time it's a schematic. So we can directly use a capacitor component in here. Let's just use it, doesn't matter. And you got two nodes. And if we name this node as P2 and this node as P1, okay, save. And you want to come back to the layout, do the same job. So it's here, right? So this one should be P2 and this one should be P1. And you want to find out that text is tiny and make it large. 200. 200 is too large, so 100. 100. And I'll do a I5 clean, LVS clean. So it's clean. So the capacitor is done. That's it. So after you have the capacitor, you have the op-amp. Let's make it connect them together because capacitor is part of the op-amp. All right, so here's not aligned pretty well. Is it? So if you see that it's not actually aligned, I want to move it up. Okay, so this time it works. Same to this one. All right, and let's see. Same to this guy. Okay, I5L, no problem. The op-amp was not done yet, right? Because we need a capacitor to be connected to the op-amp. So the op-amp is over here. So let's connect to the schematic first. So it should connect your output to this line. So we can find out the capacitor in here. I don't think we need an icon. It's just a waste of time. So now let's just find out the capacitor and directly just place it over here. It's not really long, so which is fine. And we usually we prefer P2 to be here, and so we rotate it and we make a connection to it. So I need to move all these guys. I need to move all these guys to the right. Interesting. It's not allowing me to do it. So I need to deselect that one, and now it works. Okay. And I connect the P2 to here, P1 to here. Keep in mind, P2 to VL, P1 to the other way, the other one. And go to layout. And now it's a time to get a capacitor over here. So cap is this guy. You can see how big it is. And P2 to capacitor, P2 to VL, don't forget about that. So let's connect it. P2 to VL. And P1 to here, right? So how do you do that? Because this is metal 1, so you can run a metal 2 over it and connect it to there. So let's run a metal 1 to, actually we can directly make a metal 2 connect, make a metal 2 node over over here, okay? And make it a bit larger. So for example, make it 20 by 20. Doesn't have to be that accurate, okay? And metal 1 to metal 2, let's connect it first, okay? And then metal 2 to here, no, it should be metal 2, because this is metal 1 to metal 2 connector. So metal 2, why is it so thick? I'll move this a little bit up. All right, fan out and metal 2 to here, and then connect to here. Okay. Save I5 no errors LVS match. So the op-amp, the overall op-amp, I think that's it. I don't think you can do anything else. But let's look at VL. Since we have all these inputs for the as a node for the ports, right? The ports for the op-amp, and also we need a port for VL as well. It looks weird to make the VL in the middle, so I decided to extend this VL to here. I'll do that here like this. So it should be a metal 2 node because everything else is metal 1. So that's VL. And I will export this guy as VL. But the concern is why this VL is still there, which is interesting. Because I think I already connected to here. I didn't make the connection. It made the connection. See, but why is still showing this label? Oh, it's because I created inside this this module. So, but now I move it over here. All right, so that makes sense. Let's make it smaller, like 20. 20 is fine since these guys are not that big as well. I5 L ports, interesting. So VL, oh, it's a uppercase in schematic. So I want to make this guy uppercase as well. So VL, LVS passed, I5 passed. Good news. So the chip is done with the capacitor, and so the very last step is just to place this guy into the pad frame. So the pad frame is over here, okay? And you need to know how many pins you have for the op-amp. So I have 1, 2, 3, 4, 5, 6 pins. So totally, no, yeah, 6 pins. 6 pins, then I want to use 6 pins of the pad frame. Here's one thing. You probably don't want to directly put everything here. You want to create a cheap module or library to do that, because you still remember probably how long it took for you guys to make this frame. You want to reuse it in the future. So I will get a new cell. I call it test cheap ESD and start with the layout. And in this layout view, I'm going to grab this frame in here and make it visible and make it selectable. And so you have a frame, and definitely you have all these ports. Oh, I didn't export them, so there's no ports at all. So you need to come back to your frame to export it. Okay. So for example, I have 6 pins for the op-amp. I want to use 1, 2, 3, 4, 5, 6. I want to use these 6 pins. 1, 2. So these 6 pins starting from here. And I need to export this guy and this guy, because this guy is being connected to the internal circuits, and this guy is being used for the total outputs. So when they're fabricating the chips, they need to know what are these final outputs of your chip, right? So now let's name it. So I'm gonna press Ctrl E, and I will name it as it's just the port. It doesn't matter, right? So I'll just name it as pin 1, okay, pin 1, and you want to pick it up, Control I, and make it larger. All right, so I have a pin 1. So this one you want to name it as pin 1_1. Should that be 1? Because usually we pick up this one to be 1. So this is actually pin. It can be pin 40. So now let's take a look at the pin map. I think it's over here. Let's just make it consistent. Since I don't know what are these potential problems if you don't make it right. So 1, 2, 3, 4, 5. So actually this is pin 1, this is pin 40. Let's keep it consistent so we're not having any troubles. So this is actually pin 40. And this should be pin 41, right? Pin 41. Pin 40_1, and make it larger. So let's pick it up, Control I, let's make it 100. So make it larger. And this one, let's make it, so this is pin 1, definitely it's pin 1. So Control E, pin 1, and Control I, let's make it 100. And this is pin 1_1, and change the size. And this guy is pin 2. Pin 2, and this should be pin 2, 1, and pick it up 100. Here is pin 3, and pick that up, Control E, not Control E anymore, Control I, and change it to 100. And same here, Control E, pin 3_1. All right, and pick that up, Control I, and 100. And here, pin 4. Pick that up, Control I, and 100. And same here, pin 4_1, and Control I, 100. Don't forget to save it, just in case you will lose it at some time. Control E, pin 5_1. 100. All right, so now we have all these pins for the op-amp. And again, do not put anything in the pad frame. So we're gonna reuse the pad frame. So now let's go back to the chip, which is here. So you can see the pins are available right now, okay? And I'm gonna place the op-amp in here and visible. So you can see the pins for the op-amp is available as well. So here are some tricks when you are connecting this one to these pins, because they are in the same domain, same range, and whenever you are trying to connect the wires to somewhere, you have to press Control and right click. I'm going to show you how to do it, okay? So I will do a Control J, rotate it, and Control J again, because I want to have all these ports on the top, because mainly all these pins are on the top, and I will move it closer to the pad. Okay, I'm going to zoom in to here. So now I will connect, for example, so this is VL to pin 40. So this connection is pretty simple. It's kind of effortless. And if you want to select this wire, you see, you are actually selecting the chip. So what you want to do is you want to press Control and select it and Control I. You see the width is 30. So you want to make this width to be 30 as well. Control I and change it to 30. So it looks better. Okay. And I5, no errors. It's DRC clean. That's good news. And then we want to connect from top to bottom, okay? So top to bottom, let's start from here to top. So the first one is B. You have to press Control, right? If you don't press Control, you hover your mouse to the top, there's nothing shows up. You have to press Control. See the port, it just shows up. You pick that up. So that's VDD. So when you are trying to get this wire out from the chip, you want to press Control, and at the same time, you want to press right click. So the wire is out, it just comes out. And now you want to come to here, keep the Control being pressed, and then for here to connect to this pin, you don't need to press Control, because you can see that whenever you point, you hover this mouse to this port, it shows up the little cross here. So which means it's going to be connected to here. I'm going to directly just connect it. Okay. And then the second one, Control, pick that up, and come out. Come to here, and connect. All right. So for whatever reason, this wire is super thin, but it's not a big deal. So and then VBAS 3 and 4, right? Control, not Control. Done. And then this guy. Control, not Control. Control, this is ground. Control, not Control. Save, I5 is DRC clean. You can modify the width of these wires if you like. It's not actually mandatory if you don't want to do that, which is fine. But for here, it's too close. But the thing is, it's the DRC clean, so it's actually not a problem. But I still want to change it. I don't want this one extend to both sides because that looks weird to me. And then I5 still clean. So you can see it's not really hard to make it work actually. So now let's redo this wire. This wire looks bad. No, it looks bad. Let's pick up this wire, delete it. This port, delete it. Put it here. put it here, connect. All right, so this is a lot better. And save I5 is DRC clean. So we have our first op-amp connect all these pins. Okay, and inverter. So we want to do the inverter as well. So we have an inverter over here, and I will directly drag and drop. The inverter is tiny. But before you do that, be careful. Since you do not have any other pins over here available for the inverter, so what I'm gonna do, I will make these ports available for the inverter because the inverter has 4 ports, right? VDD, ground, and what else? Input output. Okay, so I'm gonna do that. They don't have to share the same VDD and ground, but you finally have to short them together because they are being considered as one node in the schematic. So in the physical layout, you want to make them being shorted. So it's just one wire, right? So let's go to the path frame, and I'm gonna export these ones as well. So Control E. This is pin. Actually, this is pin 39. Okay. It just takes time. 100. And this one, pin 39_1, and Control I, 100. And this one, Control E, pin 38, Control I, 100. And this one, Control E, pin 38_1, Control click, 100. And this one, pins 37, pick up, Control I, Control E, pin 37_1, I, 100, here, 36, _1, I, 100, and now inverter. So the path frame is ready. Let's come back to the chip, and then drag the inverter over here. Okay, I prefer to make the top and bottom to be ground and power because that's what the inverter is designed for. And but another thing is you need to know that your input is over here. You want to connect the input here, output here, but the thing is the VDD will be inside the loop, right? You have to probably just use a connector to connect everything out from there. I don't think there's another alternative way to make it work because this is, the ports on the 4 sides, right? So now let's do it. Control click and Control click, that's metal 1, and node Control click. So that's VDD. And another one, hey, actually I can do this, right? So do it clockwise. Control click, that's V out, Control click, not Control click. Control click, not Control click. And then V in, Control click, not Control click. All right. So if you zoom in, you can find out actually it's automatically generated a metal 1 to metal 2 connector in there. So through holes to make these connections. And so the inverter is being shorted to all these paths as well. So what I want to do, I want to make draw a note here. When I'm doing a schematic, I can make sure they matches with each other. So since I5 is the I5, it's not DRC clean, really. Could imagine that. So I think this metal is being extended to the POL. That's probably why. Really? See, let's find out. Oh, so they are too close to each other. All right. So what I will do is I'll pick up this metal and short it to here. Okay. And now I5 again still. All right. So I will delete this metal and I5. So now it's clean. And I will directly do this. I5. I'm gonna no. Oh, so I can make it wider actually. So here, metal 1, and if I make the metal 1 wider, make it at the same size as this one, which is, I think it's 15, and do not extend it. Do not extend it. And I will connect this metal 1 to here. Right, it's gonna work. I5 is clean right now. All right, so let's get the schematic work as well, because I press I5 and there's no error pops up, so it's clean. So only thing left for the entire project, we're super close to get this done right now. So the very last step is just to place the op-amp and the inverter into the schematic. This is not actually super necessary if you don't really want to do that, but it just follows steps, so it's better for you guys in the future to verify the if your schematic matches with the layout. So the way to do that is right click and create a new cell, which is called schematic test chip ESD. It's a schematic. So in this schematic, I will pull this pad frame schematic over here and make it visible. The thing is, before you do that, you still need to export the same pins at whatever you did over here, right? You need to make the pins available first before you can connect the circuit to anywhere here. Okay, I will do it really quick, but you can advance the video if you like, because this is really tedious. There's no trick at all. It's just super simple. So this one should be 40, 39, 38, 37, 36, right? So let's start from pin 40. And the worst thing is we have to make it bigger, since this takes a lot of time to do this. So this one should be, the size right now should be 20, but not 100, because this is a different view. And this is pin 40_1, and you want to change the size all the time, right? Feel free to advance the video right now. It takes time. It takes time to make it work. And this one is pin 1. I hope I have a robot to do this for me, but I don't. Control E, pin 1_1. Make it 20. Pin 2. You see, probably already found out, you have to be super patient in order to make a chip. And this is just for education, just a course project. You can imagine, what about the ASIC engineers in the industry? what they are dealing with every day. It's probably thousands of times larger scale than this whatever we are doing over here. It's just not an easy job to do. But if you know how to do it, not too many people can actually replace you in the industry. You can see that the bar is pretty high. I have to go through all these analog thing, analog courses and homework assignments. Have to handle the pain. No pain, no gain, right? Have to handle the pain first in order to be able to handle something, right? So this actually applies to everywhere in the industry. If you want to get something done, right, you need to be super patient when you are doing it. So here's the principle is if you know it's going to work at some point, right? Don't be afraid of the loneliness or the don't afraid of being bored. It's going to be boring, but if you can handle that bore, right? So you can definitely being distinguished from the crowd. All right, let's do it. And finally, you find out whatever I just said is totally excused because this is just super boring. Control S and Control E, pin 39. Let's ping. Why is this chip has so many pins? Because you made it. Yeah, right. So this is what I designed. I made it to have so many pins. Oh yeah, it's 39. So the next one should be 38. And how many pins does the Arduino Uno chip has? 28, right? That's why the name is at Mega 328 because it has 28 pins, deep pins. So our chip is even more complicated than the Arduino Uno chip. So we have many more pins. And this one, close, we're close. 37. I know I just talked about a lot of things, and I just told you, feel free to advance the video, and I'm pretty sure you already did. So actually, you actually didn't know what I just said. If you are here just right now from 20 minutes ago and you don't know what I just said, you can go back and listen to that. But I can tell you there's nothing important about that. All right, the last one, ping 36, and click Control I, 20, done. Oh my goodness! But this is just one side. You have 4 sides on the chip. This is just one side, and let's come back to the chip. Right, we need to come back to the chip and connect our. So the pins are available right now in the chip, the schematic view, and we need to drag our op amp, not this one. What I'm doing here? No, I'm don't do that. Weird. So I need a op amp, which is the icon. This guy. So I want to write down something, so I'm not making any mistakes. And so what I did in my schematic is, in my layout, the chip layout here, see which one is being connected to where, right? You need to know that. If I grab my note, so the very top one is a pin 5. So pin 5 is being connected to the ground. And 4 is going to V bias 4. And 3 is going to V bias 3. And 2 is being connected to V bias P. And 1 is being connected to VDD. And V out, so 40 is being connected to V out. So this is for the op amp. And for the inverter, for the inverter, 39 is being connected to VDD, and 38 is being connected to V out, and 37 is being connected to ground, and 36 is being connected to V in. Okay, so now let's do the same thing for our schematic. Let's go to schematic, go to the chip schematic. So that's a symbol of the op amp. So now pin 5 is going to ground. We don't have the ground, so I'm gonna grab a ground over here. So ground to pin 5, ground, and V bias 4. Do we have V bias 4? Yeah, it's not V bias 4, it's VM. No, I made a mistake over here. So that's VM. It's not V bias 4, VM. VM, let's take a look. The op amp layout. So VP is on the top, VM is on the bottom. So I was thinking VP is V bias 3. So this should be VP. All right, so this is not, so part of it is not right. So this guy is VP and this is VM. Okay. And now let's start connecting everything. So go to the chip schematic. So pin 4 is going to VM. So what I will do is I'll rotate it, put it here. So VM is going to where? Pin 4, right? Control and to here. VP is going to number 3. Let's do this. And V bias P is going to number 2. Number 2. And V out, number 1 is receiving a VDD. Let's grab a global VDD here. That's for pin 1. No. Right, save. And V out is pin 40. Save. So the op amp, the connection for the op amp is done. That's it. And the inverter is over here. Inverter is this guy. So icon, put icon here. So I'm gonna rotate it. So for inverter, actually 36 is V in. So 36 is V in. Here's V in. Oh, here's V in. and V out is 38. I just directly go to here. And VDD and ground is 39, and so 39 is VDD. So I will directly connect this one, to here. And 38 is no 37 is ground. So I will do this. Where's ground? Ground is here. Okay, save. So the ground and VDD are being shorted. We need to do the same thing for the layout. So physically short VDD and ground together. So 37 and pin 5 should be shorted together. So here's 37. Here's 37. And I need to make a metal tool to cross this metal one. So you need a metal tool connector to bridge it. So now let's do it. I put a metal tool here. Okay, but actually, you know what? I'm gonna delete that because the thing is this pin directly has a metal tool connector, so I can directly use this one. See if I can get a metal tool wire out of it. Yes, it's a metal tool wire, and to here. So it's being connected to pin 5. So pin 5 is on the top. So I can actually do this, and do this. No, and do this. All right, so it's not a good practice. You want to make it looks nicer, but it's fine for now. I'm just trying to get it done since it's been taking a long time. And 37 is there, and also 39 is being connected to VDD, and VDD is pin 1. So 39 should be connected to pin 1. So this is 39. Pin 1 is, so this is not really far away from each other. So here's pin 1 and 39 pin 1. Because this is metal 1, I got 2 metal tool over here. I can directly just use the metal 1. I would just directly use this metal 1. I'm going to use this node. So it's a metal 1, metal 1, metal 1, and so do this and directly just short it. Okay. I5, no errors. L, no ports. So we need to export it because the layout has 2 ports, but the schematic doesn't have it. Oh no, the schematic has 2 ports, but the layout doesn't have. So we want to export the VDD and ground as that name. So pin 5 is VDD. You just pick it up and Control E, do VDD. Right? And ground, which is 37, right? 37. I will just pick up this node and Control E and do ground. And L, 1 port. So it's complaining that I do not have VDD, but I have a ground here. I'm pretty sure the ground is here, right? So let's see. Let's make it larger and see if this is ground. So ground has been assigned to 37, and 37 is being shorted to pin 5. Oh, I got it. So I just made pin 5 to be VDD, which was such a stupid mistake. So now let's delete that one. Yeah. And actually pin 1 is VDD. Pin 1 is VDD. Pick that pin zoom in and pick that pin here, pick it up, Control E, VDD, and then make it larger, Control I, 100. All right. Now here's the moment. I5, no errors, L match. So the project is done. If you can reach here, you show me your layout and show me your LVS and DRC claim. You don't need to do well check because here's another thing we didn't do, which is usually we want to connect all these N wells together and P wells together, and we can do it later, but not this time because it's been a lot of work. The main thing is to get DRC and LVS clean, okay? And we already did it. So spend the time to get this done and get a report done as well to get a credit. And this part, so place everything to the trip. This part is counted as a project, which takes 10% of the entire grade in this class. So hopefully you can get this done. All right. Good luck for everyone.